Now, when we talk about an optimization problem, right, there's actually different variants that we're usually not explicit about. What is, say, the independent set problem? Is it, given a graph G, what is the largest independent set? Or is it, given a graph G, what is the size of the largest independent set? Or, given a graph G and a number k, does there exist an independent set of size at least k? We don't really care that much about this distinction. It's just that algorithms usually solve the construction problem, and complexity theory is usually about the decision variant. We don't really care that much because typically it's all polynomially related. Going down the list, you can pretty much just read off the answer for the next one. In the other direction, if there's no funny business with weird problems in complexity classes, then you can usually get from decision to optimization efficiently. What I wanted to talk about today is how to get from decision to construction, in some specific cases, because it's a fun puzzle and so you can be smart about it. Let's say we have a procedure to decide satisfiability. Given a formula, it tells us yes or no. How do we now find a satisfying assignment? Let's say I can adaptively run the procedure on multiple inputs, like a Turing reduction. Here's one way to do it. First, you check the entire formula. This must be yes, or there is no satisfying assignment at all. Then, you pick an arbitrary variable and set it to true, let's say. Just substitute it everywhere. That's a valid set instance again, so we can check it. If yes, then there exists a satisfying assignment that has this variable as true. If no, all satisfying assignments have this variable as false. Remember, the entire thing was satisfiable. So substitute that instead. Either way, we have now fixed one of the variables and we have a satisfiable formula for the others. With one query per variable, we find the assignment. Let's do Hamiltonian cycle. How do we find a Hamiltonian cycle given a procedure to decide Hamiltonicity? Version 1. Same idea as for SAT. Pick an arbitrary edge and remove it. Is the graph still Hamiltonian? If yes, then there exists a Hamiltonian cycle without this edge, so we just forget about it. If no, put it back. All remaining Hamiltonian cycles use this edge. Do this to all edges, and you'll be left with a Hamiltonian cycle. The number of queries is the number of edges in the graph. Version 2. Pick an arbitrary vertex and check all of its incident edges as above, and only 2 edges will survive. Follow one of these edges and repeat the process. This effectively walks along the cycle, discovering it as you go. But now here's version 3. Let's find this outgoing edge more efficiently. For every vertex after the first, we already have one fixed, let's say, incoming edge that we are certain to keep. Rather than checking each incident edge individually, let's remove half of them. The same logic as before says that either this is fine and we can forget about all of them, or the other half of the edges are no good and we need this half. Either way, you get rid of half of the incident edges, so you find a valid outgoing edge in log of delta time, where delta is the degree of the vertex. And this is worst case n log n queries instead of n squared, which I think is kind of fun. So if you have a non-constructive algorithm, maybe you can be smart about how to use it.